Hi everyone. We talked a little bit about vector addition, and now what we want to do is we want to apply those vectors to motion in 2 and 3 dimensions. Now, I want to put a little disclaimer on this. The equations are going to look kind of crazy. Um, you guys know all this stuff already, all right? You know what displacement is, you know what velocity is, you know what acceleration is. Don't let these equations freak you out too much, all right? It'll make more sense when you actually see it in an example, which we'll have on the next video, okay? So let's talk about motion in 2 and 3 dimensions. So we know position, right, is just a location. We've been talking about just a location in one dimension, like the location on the x-axis. Well, we can have a position in 2 or 3 dimensions where it has not only a x-coordinate, but also a y-coordinate and a z-coordinate. Might not have the z-coordinate. Usually it's just x and y when we're talking about this, but we can have 3 dimensions as well, okay? So position is just a general way of locating a particle. That's a position vector that extends from a reference point. So the thing to remember also is that position is a vector, and it's going to extend from the reference point, which is usually just 0. All right. So the coordinates x, y, and z give the particle's location along the coordinate axes and relative to the origin. Again, that's our reference point, is the origin, that x, y, z equals 0. So our position vector r looks like this. It's just x I hat plus y j hat plus z k hat, where this is in unit vector notation. So if, for example, I had a position vector that was negative 3 meters I hat plus 2 meters j hat plus 5 meters k hat, that just tells me that the x coordinate is negative 3, the y coordinate is 2, and the z coordinate is 5. So if we actually drew that, it would look something like this, where, see, we are negative 3 meters in the x direction, 2 meters in the y direction, and then 5 meters in the z direction. So remember, when we're talking about a coordinate system, the z direction is coming out at you, the positive z, and then the negative z is going into the page, into the board, just depends on where we're looking, all right? But we know x is horizontal, y is vertical, and then z is forward and backward. So that was position. Now we know displacement is just a change in position, all right? So if the position of a particle changes during a certain time interval, then the particle's displacement during that time interval is our change in position, which is just going to be the position vector final minus the position vector initial. Don't let this scare you too much. All we're doing is subtracting the initial from the final point, all right, in the x, y, and z direction. So in unit vector notation, this is just the final x position I hat plus the final y position j hat plus the final z position k hat minus the initial x position I hat plus the initial y position, j hat, plus the initial z position k hat. And then you can even just rearrange this by grouping the x's together, the y's together, the z's together. This is all the same notation, all right? Again, don't let this scare you. I know it looks kind of scary, but it's really not that bad, all right? You know all this stuff already. And then you can also write that just as delta. So delta x I hat plus delta y j hat plus delta z k hat. So average velocity, we know that average velocity is the change in position over the change in time, or displacement over time. In unit vector notation, this is just the change in the x position, so displacement in the x I hat plus displacement in the y j hat plus displacement in the z k hat divided by time. And then since that time is on the bottom, you can just distribute that to each of those displacements. So you kind of split it up into these 3 different fractions right here. And that just gives you the velocity in the the velocity in the x direction, the velocity in the y direction, and the velocity in the z direction. So for example, right here, if we have a particle that moves through a displacement of 12 meters I hat plus 3 meters k hat in 2 seconds, then its average velocity during that move would just be the 12 meters I hat. So this is the displacement in the x direction divided by 2, which is just 6 meters per second I hat. So this is the velocity vector in the x direction. And then plus 3 meters k hat, so the displacement in the y direction, z direction, not y, k is z. So displacement in the z direction over 2 seconds. And so you divide 3 by 2 to get 1.5 meters per second k hat. So with our velocity vector, we have both a component of velocity and a z component of velocity. You could then find your magnitude of velocity by putting these into Pythagorean theorem and then also find the angle as well. All right, remember these I hat, k hat, j hat, those unit vectors are just giving direction. That's all they're doing. All right, so instantaneous velocity. We know that that was just average velocity without an acceleration, right? That's when we use the average velocity equation. Instantaneous velocity is when velocity is changing and we want to, we have an acceleration, so it's changing a lot. Instantaneous velocity is the velocity at a certain instant. We can write it as the derivative. We know that it's the derivative of that position, okay? Displacement. So we get velocity vector is equal to the derivative of the displacement equation. So as the position changes with time. So all we're doing here is we're just taking the derivative of the position function for x, y, and z. Again, this is just another notation to write this. If you had an equation for the position as a function of time in the x direction, an equation for the position of y as a function of time in the j direction, the y direction, right? And the position in the z direction as a function of time. You would just take the derivative of each to get the velocity in each of those directions. Again, you know this stuff already. And then of course we can just split this up. The derivative of the x position as it changes with time is velocity in the x direction, y direction, z direction. You guys can see that on the screen. And then last but not least, we want to talk about average and instantaneous acceleration. This, of course, is very similar to velocity, but instead of the change in position over time, we are talking about the change in velocity over time. All right, so we get the average acceleration is equal to final velocity minus initial velocity over time, which is the change in velocity over time. And then, of course, if we have velocity in multiple dimensions, then we will just split this up into the x, y, and z direction. So we get and that's the instantaneous acceleration. If we have an equation for velocity as it changes with time. So in unit vector notation, again, all we're doing here is we just have a x velocity, a y velocity, and a z velocity. So again, this is unit vector notation. So it's just telling you, it's kind of splitting it up into the 3 dimensions. You might not have all 3, you might just have 2, you might just have 1. And then you can put it together in magnitude angle notation as well. So this is just the same thing, all right? It's just like multiple ways to basically write the same thing. And like I said, it looks crazy right now, but on the next video, I'm going to show you a couple examples. So we'll show you an example of displacement in 2 dimensions, of velocity in 2 dimensions, and of acceleration in 2 dimensions.